So last time we did a bunch of lecturing on chapter 14. We talked about, excuse me, we talked about weak acids. Weak acids, right, because they're weak, they do not really 100% dissociate like, say, a strong acid. So what they end up doing is setting up an equilibrium. So we do have to approach these sort of problems like a traditional sort of equilibrium type problem, where we basically have to do an ice table to solve what's going on. We solve it pretty much the exact same way as we solve a regular equilibrium problem. Really, the main difference is in cases of, say, weak acids, we're interested in the pH. So when we're done kind of going through our ice table, and again, we would solve it the same way. Either, you can make an assumption, maybe it's a perfect square, maybe you got to do a quadratic formula, whatever you want to choose there, that's appropriate. When we're done, we're usually interested in the H plus concentration, and that allows us then to go into the pH equation and calculate the pH. So it really is sort of worked and formatted the same way as a traditional equilibrium problem. Again, really just that little added thing at the end that we go into our equilibrium, our pH formula, and we're able to calculate the pH of that solution. Now, the other thing we also talked about was weak bases, and weak bases, again, very similar to weak acids. Remember that when you do write the equation or the reaction that's going on for a weak base, you probably do want to include that water in there to allow it to accept the H plus. And the difference is really when you write the equation for a weak base is you should produce hydroxide on the product side. We would also solve this using an ice table. The difference here is at the end, we would get the OH minus concentration, and that OH minus concentration would allow us to go into the POH first. We could then subtract 14 to get to the pH, and then obviously you would have your answer at that point. Really, again, we also talked about, when should you maybe use a Ka, when should you use a Kb? Maybe it's a problem where you kind of have to decide that. And the real main thing that you want to look at when you write the equation correctly for what's going on, and as we talked about, that's why it's really important to make sure that you do write these things correctly. On the product side of the equation or the reaction there, you should see either H plus by itself or H3O plus, depending on which one you kind of chose there. And that should indicate there's some type of acid situation happening. And, if you're going to do a calculation, you probably should be using Ka value. Same thing here. If you kind of write the equation and you end up with hydroxide there on the product side, that also should indicate to you that it's more of a base type situation, and you definitely should be using a Kb value. Clearly, if you can identify as a weak acid to begin with or a weak base, it should kind of tell you which one to choose. But there will be problems we're going to talk about right now where, you might need to sort of pick the right one. And that's a very good way to kind of determine, which K value you should use. We also saw that, if you are given, say, a Ka, but maybe you need a Kb and vice versa, there is a nice relationship that the Kw equals the Ka times the Kb value. And that Kw is that 1 times 10 to the minus 14. And that gives you a really convenient way to kind of convert from the Ka to Kb or vice versa backwards if you need to do so. And again, you'll definitely use sort of this relationship a lot in a number of problems. We sort of finished up talking about salts, and salts are really just ionic compounds. And really, salts are generated from a reaction of an acid plus a base. Will typically get you your salt and water. So that's essentially where they are basically generated from. And as we talked about, there's really 3 types of salts that we come across. There's really neutral salts, there's basic salts, and there's acidic salts. And the way you could kind of determine whether or not a salt will really do anything is really from looking at where that salt came from. So looking at the acid and base, that basically where that salt originated from. And that goes back to sort of an important relationship that we talked about, which was, if it comes from something that is strong on the left-hand side, its partner is going to be relatively weak, and vice versa. If it comes from something that's weak, its partner on the other side would be relatively strong. And the partner on the other side is really where the salt is going to come from here. So, you know, if that salt comes from, say, group 1 or 2 on the periodic table, as we talked about, group 1 and 2 is essentially where all of our strong bases are basically located. Things like sodium hydroxide, potassium hydroxide, barium hydroxide, all those kind of guys. Those guys are going to be pretty much neutral. They will not continue to react. If it comes from, you know, a strong acid like HCl, nitric acid, so forth, that part of the salt will not react. And what we're talking about really is, in some cases, the salt has the ability to continue to react, and what it's going to continue to react with is water. So in certain cases, when you have a salt floating around in a solution, obviously there's a lot of water that's in that solution floating around as well. In certain cases, those salt will basically react with water. And if it comes from a weak acid or weak base, basically your salt, that part of the salt will continue to react, and it will react with water and really produce either H plus or OH minus. So when a salt then reacts with water, it will either accept an H plus and it would produce hydroxide, which would make the solution basic, or if the salt reacts with water and the salt sort of donates the H plus over, it would make H3O plus, and we would expect that solution to be acidic because we produced a bunch of free H3O plus. We also saw towards the end as well that certain metals, small metals that have sort of a larger positive charge like +2, +3, they also can act as acidic salts and produce an acidic solution. They could do that. Here's a much prettier picture than the thing I scribbled probably yesterday. But this is something, say, like aluminum here in the middle. We have all the waters attached. The white circles are obviously the hydrogens. The red ones there are the oxygen. And what ends up happening is one of the waters that are attached to the aluminum will end up giving away its H plus to a water that's just floating around. And when it does so, as we talked about last time, you're left with pretty much 1, 2, 3, 4, and 5 intact waters, which is why this formula looks like that. And obviously when this breaks apart, you're left with an OH that's left over there. But more importantly, what you do see that is produced is we do produce that H3O plus. So because we produce that H3O plus, we would definitely expect this solution to be acidic. Any questions on any of that stuff we talked about last time or anything like that? Okay, so why don't you give this a go, think about it for a minute or so here, and try to figure out what is the pH of a 0.45 molar potassium chloride solution. So take a minute or so and we'll kind of talk about it. Okay, so let's take a look here. So the first thing I want to look at, obviously, this is our salt ionic compound. We got a positive, negative guy. You want to think about, you know, when this is swimming around again, because it's an ionic compound, it's not going to stay together. It's basically going to produce potassium ions floating around, going to produce some chloride ions that are floating around. And really what you need to think about is both parts of the salt will either or will both parts sort of react with water that's also sort of floating around in that beaker or wherever it's at. So we want to think about perhaps where these things maybe came from. So first off, when we look at potassium, that is group 1. And group 1 is neutral salt. It will not really react with anything. So we don't have to worry about that because it's neutral. It most likely came from a base like potassium hydroxide, for example. If we look at the chloride part of it, it most likely came from an acid like HCl, which is hydrochloric acid, right? Because if you react those two things, you get water and KCl, basically. So that's sort of where it generated from. So because HCl would be a strong acid, we would assume that Cl minus would be a weak conjugate base and also a neutral base. And neither one of these parts of the salt here will react with water. So we would know that the solution should actually be neutral and a pH of 7 in that case. Actually, no calculation is needed on this particular one. Any questions on that there? All right, so why don't we try one where there actually is some calculation. So why don't you give this one a go, see what you come up with. I'll give you a hint. Do you need to do a calculation? I'll give you a second hint. Probably like an ice table should be involved there. So why don't you take a few minutes here and see what you come up with, and then we'll see if you're on the right track and we'll talk about it. Again, probably an ice table, and see what you come up with. You're sort of on the right track here. So first off, we do have a problem where we got 0.3 molar sodium fluoride. We have a Ka value for HF, which is 7.2 times 10 to the minus 4. So a couple of things when you look at a problem like this. First off, you hopefully should recognize that sodium fluoride here is a salt. And what we have going on here is some type of hydrolysis problem, which is sometimes referred to because it reacts with water. The other thing that you want to think about is, again, will any part of that salt, when it's in solution, which it breaks apart into sodium and fluoride, will any part of that salt really continue on and basically react with water through a hydrolysis problem, because water is involved? So we kind of approach the same way. We see sodium, which is really group 1, and sodium ion is a neutral ion, really because it probably came from something like sodium hydroxide, which is a strong base, which means this will be relatively weak and not go through hydrolysis. So we really don't have to worry about that. F minus, on the other hand, we do have to sort of think about where it came from. Now, a good thing about these type of problems, these salt problems, these hydrolysis problems, is they give you a lot of information sort of in the problem itself. So for example, in the problem, it says we have a Ka of HF. Because that's a Ka and that's HF, that sort of looks like perhaps where that came from. So it probably came from hydrofluoric acid. And because of that, and it's a Ka value, we know hydrofluoric acid is weak, which means that this guy should be relatively strong and will go through hydrolysis because of that. And the other thing that's really important to sort of pick up on that whole sort of event here is, because this is a weak acid, we know that F minus would be acting really as its conjugate base. And that's really important for when F minus would react with water. It's going to obviously react as a base. Any questions on that so far? Okay, so that's sort of where we want to start. We want to start with the part of the salt that's going to react with water. So that's going to be F minus. It is going to react with water through, again, a hydrolysis reaction, sometimes referred to. Now, clearly, logic also tells us F minus doesn't have an H, so it could not donate it, even if you didn't realize this whole relationship here. So clearly this got accepted because it is going to act as a base when it reacts with water. So it's going to accept that H plus. And when it does so, it will actually produce, and it always happens, it will produce where it came from, which again, this big hint sitting right here in the problem, or most of these problems, will help you hopefully get that equation written correctly. In addition, it is going to then produce OH minus as a result of the water giving away its H plus. Any questions up to there? At this point, really, before we even pick up the calculator, we can also know that this is going to be a basic solution. It should also have a basic pH when we're done calculating it. All right, so at this point, we do want to kind of go into our ice table. So initially, we would have 0.3 molar of this. Again, from the concentration of this guy, it's a 1-to-1 relationship happening here. We would have 0 this guy, 0 that guy. Change would be minus x, and plus x, which means when we get down to equilibrium here, 0.3 minus x, and x. So the ice table, very similar to ice tables we've done before. Problem most people have is, getting that equation correct here up on top. Any questions on that? Now, just like a normal ice table, at this point, we're going to put it into our equilibrium expression. So that's going to be the K is equal to our products, which is our HF times our OH minus divided by our F minus. And now here's where people run into problems as well. They want to use this number. And from our conversation yesterday or last time and earlier today, we know that we perhaps should not be using this, because when we look at our properly written equation, I see OH minus on the product side. I know it's basic. I know the pH is basic. And the third and most important thing I should know is when I do this calculation, I need a KB value, not a Ka value. So that is something where people always screw up on hydrolysis problems with salts. They go, well, they gave me the K values, probably the one I should use. And these are historically the ones where they give you kind of the wrong K value. You usually have to make sure that you get the right one. Any questions on that part of it? So to get the right K value, we want to use KW there. So I'm just going to flip the page, have a little bit more room. We could use that KW is equal to the Ka times the Kb, and that's going to equal 1 times 10 to the minus 14. And we're solving here for our Kb. So the Kb will equal 1 times 10 to the minus 14 divided by our 7.2 times 10 to the minus 4. And if we do that, there, all my extra lines. It's going to give us something like 1.4 to the minus 11 should be the value we're using. That means that we could use that and go into our KB. It's going to be x squared divided by 0.3 minus x, again, equaling our KB value, not the Ka value. We're going to assume that x is equal to 0. And that means that we would end up with x squared 0.3 is equal to 1.4 times 10 to the minus 11. Multiplying the 0.3 to the other side, doing a little square root action on it, we will end up with looks like maybe 2 point, whoops, don't write there, try that, x here. 2.04 times 10 to the minus 6 as our x value by making the assumption. Because we did make the assumption, right, we do want to make sure that we check it. So again, a reminder to check it. We would take that number that we just got. We would divide it by the number we're going to subtract it from. So in this case, 0.3 times 100%. And I believe, and probably in most cases with hydrolysis problems, you will be okay, usually on the assumption there. It's not even, I think, 1%. So the check here is good. Yeah. Let's see here.
Yeah. What was that last part that you did? To check that your assumption was correct, you divided it by 0.3 times 100? Is that what?
Yeah, so that goes back to that 5% rule that we use, right? When we make an assumption. So it's the same one that we use with our, when we did equilibrium. When we did our regular equilibrium problems in the last chapter, based on the 5% rule, what we need to do is take the X value that we got, which in this case is the 2.04. We want to then divide it by whatever you're going to kind of subtract it from, or maybe add it from to, if it's that case, and then times it by 100. Again, if it's less than 5%, you're all good on that assumption. If it's more than 5%, then you have to go solve it some other way, like, quadratic formula or something like that. Again, just like anything else, if you want to go straight into the quadratic sort of formula, you could, and skip the assumption. It's just probably a little bit more math, but here you definitely want to check it. And like I said before, I would say probably in most cases you should still check, but probably in most cases with hydrolysis problems, you'll probably be okay in terms of the assumption. It usually will check out okay, but it does go back to that 5% rule. Other questions? I think the other question was answered, but again, this 1 times 10 to minus 14 is our KW constant value for it, basically. All right, there. All right, so now that we checked it, now that we got our X value there, we want to then go back to our ice table just to verify what we're dealing with. And the other important aspect of it is if we go back to our ice table, we see that the X value is not the H plus concentration, but in this case, it is the OH minus concentration. So what that's going to allow us to do is that this is actually, again, our OH minus concentration. So that will get us our POH of our 2.04 times 10 to the minus 6. And that's going to get us a POH of something. Let's see here. 5.69. Now, again, if for some reason you thought this was the pH value that you just calculated, it should not make sense because we already determined that the pH of the solution should be basic. And obviously 5.6 would not be a basic pH if you misunderstood and thought it was the pH value. So we do need to subtract our 14 there to get to our value there, and we end up with 8.31 as our pH value. And that 8.31 is a basic pH for sure. And it does make sense based on what we're talking about there. Any questions on that there? So places, again, where people really kind of go bad on these sort of salt or hydrolysis problems is they're not sure how to correctly write that equation. So for example, I've seen people in a problem like this end up with H3O plus on the product side. They use the Ka value when they should be using the Kb value. And again, they just don't realize sometimes it's the OH minus you're getting, not the H plus, and they go right into the pH. Any questions on any parts of that problem there? Okay, so why don't you try one more here, kind of see what you come up with. We've got, what is the pH of a 0.75 molar sodium cyanide solution, Ka value for HCN given to you. So take a few minutes, see what you come up with. All right, so let's see how we're doing. I think that sounds about right, but let's just see how we get there. So we're looking at sodium cyanide. And again, what we want to do is recognize hopefully that as a salt. So we want to make sure we understand, obviously, when it's in solution, it is going to break apart into our sodium ion and our cyanide ion. And again, we want to think about, which part of this, if any part, will continue to react with water. As we talked about a number of times at this point, sodium, which is group 1, is neutral, so we don't have to worry about it. Again, the Cn minus here, if you're not familiar with where it came from, the problem itself, again, gives you a pretty good piece of information. We were given the Ka value for HCN, Ka obviously indicating that that's a weak acid, which means that guy there would be its partner and act as a base or a conjugate base. So we would expect that because this guy is weak, that the Cn minus would be relatively strong, and we would get that reaction between Cn minus and water. And again, understanding that this is really going to be sort of the conjugate base and act as a base, that's going to help us understand that it's going to pick up that H plus. Again, common sense also tells us there is no H for it to give, so it's got to pick it up. So we'll end up with HCN and OH minus. And again, you can see a couple of common themes that occur in these problems. HCN is, where it came from is always what you make. And secondly, here again, we see our OH minus. So without even doing the calculation, we know it should be basic. We also know that we should be using a KB value here. And we obviously don't have the KB value. So we do need to switch it around to make sure we do have the right one. So that KB is going to be our KW divided by KA, which would be 1 times 10 to the minus 14 divided by our 6.2 times 10 to the minus 10. And that would get us a KB value of 1.6 to the minus 5. Any questions up to that point there? All right, so now we really pretty much have everything that we need to solve this. So I'll just rewrite the equation here. So Cn minus plus some water. So initially, the source of Cn minus comes from the sodium cyanide, and it was 0.75, 0 and 0. Change minus x plus x and plus x. That means at equilibrium, 0.75 minus x, x and x. Just like we talked about previous as well. Again, I'm not going to put anything here, so I'm not tempted to start using numbers or something where I shouldn't use them. As we talked about in the last part of this, this is again a KB. We know it's a KB because I do see OH minus on this side. And we have HCN, OH minus, and CN minus. Again, because it is a KB, we want to make sure that we use the right value, which is our 1.6 times 10 to the minus 5. Putting in our values there gets us x squared divided by 0.75 minus x equals our 1.6 times 10 to the minus 5. We can make our assumption here that x is equal to 0. That's going to get us x squared over 0.75 is equal to 1.6 times 10 to the minus 5. Obviously, we're going to multiply the 0.75 to the other side and also square root it. And looks like maybe 3.5 to the minus 3, give or take. We also want to make sure that we do check it. So if we divide it in this case by 0.75 and times it by 100, it's like 0.4%. So again, the check is good here. And again, you would take 3.5 times 10 to the minus 3 divided by 0.75 times it by 100%. And again, I think it's like 0.4% or something like that. So we're all good on that. Again, important to remember from our sort of ice table here, X again does not equal the H plus, but in this case, it does equal the OH minus, which would be our 3.5 times 10 to the minus 3, allowing us to go into our POH first. And that would get us a POH, maybe like 2.46. Getting our pH by subtracting our 14. Gets us, I think, what was asked before, 11.54 as our pH. And that does make sense as it is obviously basic in this particular case. Any questions on that? Yeah, so again, we want to make sure we use the KB value as was correctly answered there, because we do see OH minus on the product side. And that's why we cannot use the Ka value that's given to us. And usually in these sort of hydrolysis problems, they will give you the Ka value when you need to use the Kb value usually, and vice versa. So as I was mentioned many times, it's really important to know how to correctly write these equations, because, you know, if you're not sure how to do them or you don't do them correctly, I have seen over the years many people, again, even on something like this, end up with H3O plus on the product side. So, you know, it's really important to make sure you know how to do that, because obviously it can throw your whole calculation off, obviously, by using obviously the wrong K value. So this,
Professor,
yeah, go ahead.
I got a similar pH, but the part where you're looking for the concentration of OH, when I plug into my calculator, I'm getting something different.
And I rounded, so I don't know if maybe if you didn't use the rounded number. So let's see, where's that number there? Maybe that number there.
So every time I do it, I get 4.6 to the 10 negative 3.
For
times 10
the
to negative 3.
for which one now?
For the concentration of OH.
For concentration of OH. Okay, so we're gonna just double check. So you would want to take 0.75, right, and times it by 1.6 to the minus 5.
Yes.
And then take the square root of that.
Okay, I see what I did wrong.
Forgot the square root, maybe. Yeah, so make sure you take the square root, and you should get the 3.46 times 10 to the minus 3.
Okay, thank you.
Well, other questions? Okay, so again, super important to make sure that you can write these things correctly. And again, these are the little things in this class where, you know, if you just kind of make that little error, kind of throws everything off. So you want to be really careful when you do that. We did a couple examples here, obviously, of salts that produce hydroxide. They're basic. If we did have an acidic salt, you would approach it the same way. The only real difference in that one is it would produce H3O plus on the product side. And at that point, that would be your H plus. You could go right into the pH. So if you have a salt that produces H3O plus, worked out the same way, probably as well. In addition, instead of maybe getting the KB value, you would need to get the Ka value in that particular case, still using Kw. But the main difference would be you would have H3O plus on the product side, go right into the pH equation at that point. Don't have to do the POH. Any questions on salts? How to do calculations of pH involving salts? Anything like that? Okay. So let's just kind of finish a little bit talking about salts, just a little bit more. Up until this point, sort of the examples we looked at, only one part of the salt, had the ability to react with water. It is potentially possible that you could come across a salt where both parts could actually continue to react with water. So for example, here, go that way, maybe. So let's just say we had a salt like, we'll go with ammonium nitrite, something like that. So if we look at ammonium nitrite and we look at that salt, when it breaks apart, you have NH4 plus and NO2 minus. Now, when we analyze both of these salts, this guy here most likely came from NH3, and that is a weak base, which means this would be a relatively strong conjugate partner in an acid. And this guy would actually then continue on and react with water. If we look at something like NO2 minus, NO2 minus probably came from an acid like HNO2, which is not nitric acid, but nitrous acid. And that is also a weak acid, which means that this would also be relatively strong and a base and would also react with water at the same time. So it is potentially possible that you could get a salt where both parts of them can continue to react with water and produce either H plus or OH minus. Obviously, if you try to do those calculations separately, it's fairly complicated to do so. So sort of the general rule that we kind of follow when we get to a situation like that is we compare the Ka value to the Kb value for what's going on. And we use that to determine whether or not we would expect the solution to be acidic, basic, or neutral. So in comparison, if you compare the Kb value for the anion, the negative guy, and it is larger than the Ka value for the positive guy of the salt, you would assume that the solution would be basic, and you would just do the Kb calculation. Same thing would happen if the opposite was true. The Ka value for the cation was larger than the anion. You would assume that that solution would be acidic and pretty much just do the calculation for the Ka value. If they happen to be pretty close to each other, I wouldn't do a calculation. You could probably just assume that it's going to be neutral. So personally, I don't think we'll probably come across too much of that here. Maybe in the textbook or online, maybe you might come across it. But if we are dealing with a salt where both parts will go through hydrolysis, look at the Ka value, look at the Kb value, and whichever one's larger, that's sort of the calculation that you should do. Any questions on that there?
Yeah. So if we let's say that the Kb is stronger than or more than the Ka, we calculate the concentration of OH instead of calculating the concentration of H plus.
Exactly. So basically, what we would assume is that's maybe the predominant thing that's sort of happening in that solution in comparison to both parts of the salt, and probably in that case, it would maybe be producing more OH minus. So it's truly still happening, the other guy, but you would probably ignore it and just look at the contribution of the OH minus as sort of what's going to probably make the pH for that solution, and you would do the Kb value and solve for OH minus. And the same thing would be true for the Ka. If it was larger, you would ignore sort of the OH minus contribution and just figure out how much H3O plus is being made and assume it would be that. Truthfully, it's very complicated or very way out of our class here or need if you want to separately kind of sort of calculate all those things and take into account everything that's going on. So this is sort of the general rule that most people will follow when you do come across a salt that, both parts could go through hydrolysis. Other questions?
Thank you.
You're welcome. Okay, and here's just another table, I think maybe similar from your book, that kind of explains what's going on here. And again, I personally don't anticipate probably giving you one where both would go through it, but you may come across it somewhere. And our table here, I think, to talk about. And this is just a table again from your book. You have a similar one there in our edition, and it just talks about all the stuff we talked about in terms of salts and stuff like that. All right, any questions on salts to finish that up with? Yeah. Okay. All right, so the next thing we're going to talk about then is oxides. Oxides are basically, elements that have oxygen in it, hence oxides. This is a sort of a table of some oxides and what they commonly will make. And what we see is sort of what we would expect, if we take some of our group 1 over here or group 2, and they have oxides, you react it with some water. This is, really how we get our bases, right? Like our NaOH or KOH and those type of thing. So group 1 and group 2 are considered basic oxides. When they react with water, they typically will produce bases. On the right-hand side where we have sort of our non-metals happening, these guys over here, for the most part, are what are referred to as acidic oxides. And that's because when they react with water, they form acids. Like two examples on the bottom here, CO2, which is carbon dioxide when some water makes carbonic acid, and N2O5 in some water makes some nitric acid. So those are referred to as acidic oxides. We do have some of our orange guys here. Orange is amphoteric, and they can go both ways. They either can sometimes, when they react with water, make an acid, or react with water and make a base. So they can't go either way. So kind of left-hand side where we sort of been talking about, that's sort of where we expect to find basic type stuff. Right-hand side, kind of we find our acidic oxides when they react with water. Any questions on that there? All right, the next thing we're going to talk about, we've now talked about maybe a couple of definitions of acid and bases. The Uranus definition of an acid is something that will produce H plus or H3O plus in water, or OH minus in base. The Bronsted-Lowry definition is one where a acid is a proton donor, a base is a proton acceptor. So we're going to have a sort of third definition of an acid and base, and that's our good friend Lewis. And perhaps you remember Lewis. When you think about Lewis, those are like Lewis structures. And when we think about Lewis structures, we think about electrons, right? And bonding and all that kind of stuff. So definition of a Lewis acid is a substance that can accept a pair of electrons, while a Lewis base is a substance that can donate a pair of electrons. So kind of opposite of Bronsted definition in terms of accepting and donating, and we're also opposite in terms of, we're talking about electrons when we talk about a Lewis acid and a Lewis base rather than the H plus. So when we have something that's a Lewis acid, it basically, a lot of times, good Lewis acids are things that are sort of polar and they have non-bonding electrons, or things that have a negative charge, right? Because when they have a negative charge, they've gained electrons, which means they have electrons to sort of give, and vice versa. Here, a Lewis base is typically something that can accept a pair of, accept a pair of electrons, a Lewis acid. And something that's good like that is something that is deficient in electrons. So things with positive charges, things like boron, which is electron deficient. And in case I misspoke, the Lewis base is the guys that are typically negative things, and things that have lone pairs that are polar. So here's an example again. Here are H plus, and obviously for it to be H plus, it obviously had to lose electrons. It's electron deficient here, which makes it a Lewis acid. OH minus has got a minus, it's got some lone pairs, it's able to donate it to, and we make water there in our acid and base. Still the same definition from Bronsted-Lowry in terms of determining which one's the acid and which one's the base. Obviously, the acid is something that donates the H plus, so the Bronsted definition would be something going on like that. And accepting the H plus would be the OH minus, which would be the base. So it does give you the same answer if you look at it in the Bronsted sort of definition versus the Lewis definition. But again, one is talking about electrons and one is talking about H plus donation. Same thing here. Our H plus is deficient in electrons, makes it a good Lewis acid. NH3, which is polar, has got those lone pairs on the nitrogen, able to donate them in, and that makes it the base. Again, same definition. If you look at it in terms of the H plus would be donating the H plus, making it the acid, while the NH3 would be accepting it, making it the base. The nice definition, though, about a Lewis acid and base is we could look at acid and bases without having to have any H plus being accepted or donated. So here, if we look at BF3, which is an incomplete octet, right? Boron is notorious for having less than 8 electrons, making it electron deficient. Again, our NH3 being polar and those non-bonding electrons able to donate it over, making it the Lewis base, while the BF3 is our Lewis acid in this case. And now we have sort of a definition of acid and bases that do not involve any type of proton like we commonly think about it in terms of Bronsted-Lowry definition. We definitely will see Lewis bases a lot throughout the semester here. We will see them when we talk about transition metals. We'll also see them when we talk about complex ions and stuff like that. So again, Lewis base, something that can donate a pair of electrons. Typically things that are polar and have those non-bonding electrons are able to kind of do that, are something with a negative charge. So like OH minus, Cl minus, these are all things that are good sort of Lewis bases. H2O as well is also a good one. If you look at water, it's got those non-bonding electrons, it's polar, and it makes it a good Lewis base as well. So we'll see it definitely pop up a lot, Lewis bases, especially when we get into those sort of complex ions, coordination complex a little bit later on in the semester as well. Any questions on the Lewis acid base definition? All right, so the last thing I think we're going to talk about here in this chapter is the stuff that we sort of skipped a little bit earlier. We're going to talk about what happens with polyprotic acids. Polyprotic acids are acids that basically have more than one H plus to give away. And again, we talked about ways we could represent acids. HA means that when it goes apart, H plus and A minus, that is what is referred to as a monoprotic acid. Something with the ability to give away two H pluses is what is sometimes referred to as a diprotic acid. And something like that has three H pluses it could give away is known as a triprotic acid. Important, and I think we touched upon it earlier in this chapter, is when something loses an H plus, they actually do come off one at a time. And that's why when we talk about acid conjugate base pairs and so forth, the only difference is one H plus. So for example, if we looked at phosphoric acid, again, the first thing that would happen is the first H plus would come off, leaving us H2PO4 minus. And it would have a Ka value for that. Ka1 is sometimes referred to. The next thing that would happen is that H2PO4 minus would drop off another H plus, giving us HPO4 2 minus. And that would also have a Ka value associated, which is Ka3. The last thing that would happen is that last guy there would then drop off the third hydrogen and leave us with phosphate, which would then have a Ka3. And sometimes when we think about these reactions, we think about like the overall reaction that's happening that you get when you add all these together. If you add all these together, this cancels, and you're left with the overall reaction we sometimes think about, which is H3PO4, 3 H pluses on the product side, which is over here, and our phosphate. So sometimes we think about these things as, oh, they must all drop off right away. All three of them must come off because we think about the overall reaction, but it really is a stepwise reaction where we have each of the H's coming off one at a time. We also know that perhaps it is much easier to remove the first H plus than it is the second, than it is the third. It gets harder as you go through it. And you can see that by the Ka values that we see here. This is something like 7.5 to the -3 for the first H plus to come off. Then the Ka value for the second H to come off is like 6.2 to the -8. And then the third one, 4.8 times 10 to the -13. The K values get smaller after each H plus comes off. And that means that it is smaller and we mainly have reactants there in those steps, which means not a lot of H plus is coming off in each of those steps. Again, it just gets harder because when you remove that first H plus, you're then left with something that has a negative charge, and then you're trying to remove something that's H plus as well, positive, negative. It kind of holds it a little bit tighter, makes it a lot harder for that second H plus to come off. And then obviously you build up a -2 charge after that, for example, makes it harder for that third one to come off. So here's a table from your book. And again, you can see that each of them have K value for each of the hydrogens to come off. This is, as I was mentioning before, probably the only place you'll see a strong acid like sulfuric acid, H2SO4. And you can see it gives you a very useful number of, oh, that's a really large number. So again, the reason it's really on there because that second one, that HSO4 minus we talked about, is a pretty weak acid. So it does have a value. So we do consider that sulfuric acid to be a strong acid, but the kind of second part of it, when the first one comes off, that HSO4 minus is a weak acid. Any questions on that?
Professor, I have a question.
Yeah.
Are we allowed to use, like, have that chart with us when we take the exam?
No and yes. So no, you shouldn't have your own, but if you needed any of those values, it would be provided for you.
Okay, cool. Thank you.
You're welcome. Yeah, so any type of value from like a table, Ka value table, Kb table, or something like that that you would look up would be provided for you on the exam and stuff like that. Other questions? Yeah, so you don't have to memorize the Ka values. I personally don't know what they are either, so don't memorize them or anything crazy like that. So this is some of the stuff that we sort of talked about. Again, there are acids that obviously could give away more than one proton, which is an H+. They do it one at a time in a stepwise fashion. Again, much easier to remove the first one than the second or third. And let's take a look at an actual calculation, and we'll do it here together just to show you sort of how you go about this. And we're going to change the problem just a little bit. We want to know, when we're all said and done, what is the concentration of H3PO4? We'll want to know what is the concentration of H2PO4 minus. We'll want to know what is the concentration of HPO4 2 minus. What is the concentration of PO4 3 minus? What is the concentration of H plus, and what is the pH, right? So we'll add all that to it. So in a problem like this that I just made up here, that we want to pretty much figure out what is going on here with everybody at equilibrium, we do need to approach it really as sort of three separate problems. The Ka1 is going to be for when that first H plus comes off. So that's going to be when we have our H3PO4, dropping that first H plus and our H2PO4 minus. The Ka2 will be for when that second one comes off. And the third one is for when that third H comes off. So based on the way that I kind of wrote everything, we're pretty much looking for everybody's concentration. So we're going to start with the first K, and that's where we're going to start. So we're starting with a 5 molar solution of phosphoric acid. So taking our first step here, which is the 5 molar H3PO4. So the first thing that's going to happen is that H3PO4, as we just wrote, will break apart into our H plus and our H2PO4. And that's going to be our Ka1. So initially we do have 5, so we do need to do a nice table. We're going to do 0 and 0 here. The change is going to be minus X, plus X, and plus X, which means when we reach equilibrium, we would have 5 minus X, X, and X. So ice table, pretty similar to sort of what we've done before. Since this is just the first H plus that's coming off, we would do our Ka1 relationship, which is H plus times H2PO4 minus divided by H3PO4. And that is going to equal our Ka1 that we could get from that table or the problem, which was 7.5 times 10 to the minus 3. Just like we've done before, we're going to put our stuff in. So that's going to give us x squared divided by 5 minus x equals 7.5 times 10 to the minus 3. We're going to give it a go and assume that x is equal to 0. That will give us x squared over 5 is equal to 7.5 times 10 to the minus 3. And if we do that, we got 5 times 7.5 to the minus 3. We want to make sure we take the square root of it. And it looks like we end up with an x value of 1.9, we'll call it 4, times 10 to the minus 1, We do want to check it. So we would want to check it by taking 1.94 times 10 to the minus 1 divided by 5 times about 100. And I hope it's okay. It should be because I made sure. So it's 3.8%. I didn't feel like doing the quadratic at this point. So 3.87%. So it is a good assumption. So that gives us our X value. Any questions so far on this table here? So very similar to, you know, sort of the ice tables that we've done before. Now, if we look at that X value, it does give us some information now about everything we're looking for. We see that the H plus concentration is equal to X. The H2PO4 minus concentration is equal to X. So right off of the first table, we have the concentration of H plus, which would equal the concentration of H2PO4 minus. And that's going to equal our 1.94 to the minus 1 molar. So that takes care of this guy and this guy so far. We also see from that first table that if we take 5 minus X, that will give us the equilibrium concentration of our phosphoric acid. So if we do 5 minus 1.94 to the minus 1, gives us 4.81, we'll call it. So we have this guy, which would be 4.81 molar. So off of that first table, we were able to pretty much get 3 concentrations, which is good. We're still, though, interested in HPO4 2 minus, which means I see that over here. And I'm sorry, over here. So that means the next thing that I want to do is go to the second step that's going to happen at this point. So we'll do that next. So the second step that's going to happen is our H2PO4 minus will then lose its 2 H pluses, or 1 H plus, I'm sorry. And we'll end up with a 2 minus. And this is the second H that's going to come off. So at this point, we're dealing with the Ka2 value, which was 6.2 times 10 to the minus 8. All right. So we need to do an ice table as well. So our ice table here, when we look at H2PO4 minus, if we go back to our first table, we actually do have a value for it, and it is the X value from the first table is where we're going to get that. So that would be 1.94 to the minus 1. When we get to the H plus, if you look at the first table, we also have a value for H plus that's going to be here. So this is not going to be 0 on our next table. It's actually going to have a value which would also be X, which would be 1.94 times 10 to the minus 1, and this guy would be 0. Any questions on that initial part there? Rest of the table should be fairly similar, minus X, and plus X, which means when we get to equilibrium, 1.94 times 10 to the minus 1 minus X, 1.94 times 10 to the minus 1 plus X, and X. This again is going to go into our Ka2 expression, which would be H plus HPO4 2 minus divided by H2PO4 minus, again equaling our 6.2 times 10 to the minus 8. That's going to give us up on top, let's see here, 1.94 times 10 to the minus 1 plus X times X divided by 1.94 times 10 to the minus 1 minus X equals 6.2 times 10 to the minus 8. Minus will make the assumption, since we've done it before, X is equal to 0. That is going to give me 1.94 times 10 to the minus 1 times X divided by 1.94 times 10 to the minus 1 equals 6.2 times 10 to the minus 8. I think I could do this math. That is going to get rid of each other. And that's going to give us an x value of 6.2 times 10 to the minus 8 by making that assumption. We do want to check the assumption. So we'll go with 6.2 to the minus 8 divided by 1.94 to the minus 1, times it by 100, and it's like nowhere even near 0.1%. So the check is good on this. So in terms of answering some of our questions, let's take a look at what that means. Our HPO4 2 minus is equal to X. So if we add that back to our little tally here, our HPO4 2 minus equals X in this case, which is 6.2 times 10 to the minus 8 molar. Now, there's also two other things on this table. What happens to the concentration of H plus at this point when we lose the second H? And what happens to H2PO4 when we lose the second H? If you put your X value back into both of these places, the concentration stays the same. It really doesn't change. So if you take 1.94 times 10 to the minus 1 and add 6.2 times 10 to the minus 8, you pretty much end up with the same. And same thing here. So it won't change by putting it in there, which means our concentrations that we got from our first step are still good for these guys. Any questions on that? So that takes care of this guy in terms of the concentration. That leaves us one last concentration we're really looking for, which is phosphate. In order to get the phosphate, we need to go to the third step here where this guy loses the H plus. So that will be the third step we'll do. So the third step is at this point HPO4 2 minus, dropping off the last H plus to form the phosphate, which is what we're looking for. Again here, that is Ka3, the third step of losing it. Just like we did before, we need to reference back the previous table. So we do know that from the previous table, the HPO4 2 minus concentration is not where I drew that arrow. It's actually this arrow. There we go. Is 6.2 times 10 to the minus 8. So that would be our initial on this table. Just like before, we still have some H plus floating around from the first table and this table, and it's still 1.94 times 10 to the minus 1. And 0 for our phosphate. Change going to be minus X plus X plus X, which means at equilibrium 6.2 times 10 to the minus 8 minus X, 1.94 times 10 to the minus 1 plus X and X. Any questions on the ice table here? So important here that we go into our Ka3 expression, which in this case is H plus PO4 3 minus divided by HPO4 2 minus. Again, making sure that's equal to our third Ka value, 4.8 times 10 to the minus 13. Putting it in there gets us 1.94 times 10 to the minus 1 plus X times X divided by 6.2 times 10 to the minus 8 minus X is equal to 4.8 times 10 to the minus 13. We've been good on the assumptions all problem here, so might as well do it one more time. We're going to assume that X is equal to 0. That's going to reduce this down a lot easier. Going to give us 1.94 times 10 to the minus 1 times X divided by 6.2 times 10 to the minus 8 equals 4.8 times 10 to the minus 13. We're going to multiply the bottom to the other side. So that's going to be 6.2 to the minus 8 times 4.8 to the minus 13. We're then going to divide it by 1.94 to the minus 1 That is going to get us a 1.5 to the minus 19 as the X value. You want to check it, but it pretty much should be good. 1.94 to the minus 1 times it by 100, nowhere even near 1%. So the check is good here. Again, what that means in terms of our table is obviously that X value is our PO43 minus, and we could add that to our list here. So our our PO43 minus concentration 1.5 times 10 to the minus 19 molar. And let's see what happens with everybody else. Again, if you go back and put that X value into this equilibrium line, this number is not going to change. This number is not going to change either. It will still remain the same, which means essentially we now have everything that we need except for to calculate the pH. But more importantly, what we see is as we go from the first H plus that comes off to the second H plus, it goes from an H plus concentration of 1.94 times 10 to the minus 1 or 0.194 to basically only like 6.2 times 10 to the minus 8 comes off in the second step, and even less comes off like in the third step. So what we see with our calculation here is what we were talking about, that the majority of all the H plus that will come off in a polyprotic acid is that first step. So that first step is probably where in most cases you would get that the amount of H plus is going to come off. As you can see in this example, second step, third step, very minimal amount is basically coming off in terms of the change part. So the majority of it that comes off will be in that first step, which means if you were asked a question where you weren't interested in like all this and you were just interested in the pH, it would probably be pretty safe to just do the first step, get the H plus concentration and calculate the pH, which we should do as well. So the pH in this case minus the log of 1.94 times 10 to the minus 1, going to get us a pH of 0.71, we'll call it. It's acidic. It is an acid, so I guess that makes sense as well. So a couple of things on these type of polyprotic acid problems. They're basically ice tables, kind of the equilibrium line from one step becomes your initial line on the next table. And again, if you're not asked like we were here in this problem for like everybody's concentration, all you need is the pH, probably just do the first step, just do like this calculation. And then probably 9 times out of 10, you will be okay to figure out the pH from that first step. Again, because the majority of all the H plus that's going to come off will happen in that first step. Question on polyprotic acids.
Professor?
Yeah.
Why is the phosphoric acid's concentration 4.8 instead of 5?
It's at equilibrium. So when it's in solution, basically this first part's going to happen, right? So it's going to lose some of its concentration because some of it went off and dissociated into H plus and H2PO4. So what's left when sort of the thing reaches the equilibrium is whatever it was, 4.86, and it's just that little bit that comes off. Again, it's a weak acid, which means not a lot is going to come off, but that little bit that does come off will basically come from the initial concentration when you pop it in there.
Can you show me the calculation?
Yeah, it's right here. It's actually this calculation. So it's this part here at equilibrium.
Oh, and you just okay.
We put the X value in. So the X value represents basically how much of that H plus came off. So when you put this in solution, when it finally kind of comes to equilibrium, it's going to lose some of that H plus coming this way, which is going to start at 5, but pretty much end up at like 4, whatever it was, 4.86. So it'd be the 5 minus the 1.94 times 10 to the minus 1.
Okay, thank you.
You're welcome. Other questions?
So, Professor,
Yeah.
So in a question, for example, if we were to ask to find only the pH, we won't need to find Ka2 and Ka3.
Right. So in most cases, I won't say 100%, but probably most of the time, pretty close to 100%, that if you're given a polyprotic acid, say like phosphoric acid, whatever other one it might be, carbonic acid, whatever it should be, if all you're really asked to solve for is the pH of that solution, is probably almost all the time pretty safe just to do like the first step we're looking at here on the screen. And that's going to be really your majority of H plus that's going to come off into solution, and you'd be probably pretty safe just to do that. You wouldn't need to go into say Ka3, A2, or A3 if you weren't asked specifically, like, you know, other people's concentrations along the way. So pretty much when you put a polyprotic acid into water or into solution or make it, you know, the majority of all that H plus that's going to be free floating is probably going to come from that very first sort of step. So yeah, so it's pretty safe. Only pH asked, just do the first step, get the H plus concentration. Because as we see in this example, it really doesn't change all that much as you go kind of from step 2 to step 3. You're only losing a very, very, very small amount that probably would get lost in rounding anyways. Other questions?
Could you go back to the previous slide really quick?
Yeah. That
Thank
one?
you.
Yep. Any other questions on anything there? All right, so we went a little long, sorry about that, but we're kind of in the middle here. This actually does wrap up chapter 14, which means that we will have the exam on Wednesday of next week. So a reminder, Monday's a holiday. In case you have classes tomorrow, I think Thursday is a holiday as well, I think, so oddly. No class on Monday because it's, I think, President's Day, right? And so we'll come back. Obviously, we have lab today, but in terms of the exam, we'll take it next Wednesday, 1 week from today. It'll be on chapter 13 and 14. You will not be given any formulas, but any values like Ka values, you know, those type of things, table values would be provided for you. We will probably take it just like we did the quiz. So it'll be sort of exact same sort of setup. You could go print it, come back, or use paper to do it. And again, no notes or anything like that. Probably mostly, I would think, problem-based type questions would be my guess, similar to the quiz. The quiz will be graded pretty soon, next day or so. I'll put it up on Canvas. I just haven't got a chance to finish them all. So probably in the next day or so, it should be up there for you to kind of see how you did and take a look at it, if that's the next question.